Hello. Hi guys, good morning. Welcome back to a new video. In this, we're going to see problem number 3180 and 3181. Both are same, just improvisation in the constraints. It is exactly, if not exactly, but yeah, like more or less same than this problem. DP also, and also the bit set tricks. We're going to see it is same as that of this problem. Now, before moving on forward, we have a target 35k subs before June end. करवा देना यहाँ से. Now, this will teach you everything about BitSet tricks. What a BitSet is. Again, for Python folks, no need to worry. For this, for you guys, this crash course is more than enough. But for C++ folks, I'll explain everything. Now, coming on back, the problem is maximum total reward using operation show. Again, the video will be a bit long because actually it is very long. So you can see it's going to be long. Now, coming on that, the problem simply says that you are given an integer array called as reward values of length n, representing the values of rewards. So you can just imagine, I will more or less sometimes will say reward values as nums of I, right? Because this is simply an array of nums. So as to just make it sure, like remember, okay, I can refer it as nums of I also, like nums array and like that. Now I have initially the reward x is 0. So I will represent that as reward sum. Initially for me the reward sum is 0. Now we have to choose any unmarked index from this nums array, and again the entire array I can choose which is initially unmarked. As I choose it, I will make it mark. And how I can choose it? I can choose it, and when I choose it, I will say in my existing reward sum, I will add the existing nums of I. And I want to maximize my total reward value which I can get, which is this sum I want to maximize. Now you can simply see that what you will do for this example case, you can take 1 and 3. Again, there's a slight condition of when you can take some reward. You can take any reward value which is nums of I in your case. You can take that only when the existing sum whatsoever you have been getting, the existing sum, reward sum whatsoever you have been getting, it is less than this nums of I. Only then you can take your reward value of I. Cool. Now coming on back, so far we let's say take 1. So my reward sum is 1. I can take a 3 because 3 is more than my reward sum. Reward sum was 1, 3 is number. So I can take 3 also. Now the reward sum has become a 4. And this is the maximum what I can get. So answer is 4. Now in this case, I can take in the very beginning, I will take 1. Right? Okay. Next. Okay, so far the reward sum is 1. I will take then 4. Now, why I can take 4? Because reward sum is 1. I have a 4. I'm taking 4. 4 is more than 1. So I can take my 4. Okay, if I take my 4, reward sum has become 5. I can take my 6 because 6 is more than my 5. I take my 6. Reward sum has become 11. That's the maximum reward sum you can get. Answer is 11. So you realized ultimately what you are doing. You have this sequence. You can take any subsequence out of this sequence, but Aryan, the subsequence need to be ordered. But in this case, the subsequence is 164. But you told us the sequence of numbers should be 146. Yeah, make sure. It's obvious that we should sort the array, sort the input rewards value of array so as our values are always increasing, because the prime condition is reward sum should be less than that of what I am right now about to take as reward value of I. So it's obvious I will sort my input array. After sorting, I know it's one sequence out of which, again, let's say it is sorted 1, 2, 3, 4, 6, 4. So you took 1, 4 and 6. You took these numbers. So you realized you have to just simply generate a subsequence having the maximum sum. That is your, and how will you generate the subsequence? The subsequence should be generated such that existing reward sum whatsoever you have got, again, let's say the subsequence is 1, 2, 3. This is not the valid subsequence. Why? Because 1, reward sum is 1, which is less than my 2. Okay, I can take 2 also. Reward sum is 3. It is not less than my 3. I cannot build the subsequence. So you realize ultimately your task is, from this input sequence, after sorting it, you will generate a subsequence, and then you have to maximize the sum of that subsequence. It's simply that how you simply go and generate a subsequence. You have an array, input array. For every index, you have 2 options. Take it, not take it. So in brute force way, when you will generate all these subsequences, you will take a 2 to the power n time. But we know that these kind of problems are very basic for DP. which means take, not take. So we will simply say, okay, for this index Aryan, I will have two options. Either I will take it or I will ignore it. So for this index, again, nums of I, which is rewards value of I, I will either take it or ignore it. Now, if I ignore it, then I should directly go on and jump on to next index, and my reward sum will remain as it is, whatsoever it was previously. But if I take the specific index, firstly, I have to make sure that my reward values of I, which is this value, again, nums of I, and I'm saying I'll change it, I will use it interchangeably. This is more than your existing reward sum whatsoever you have got. This is the reason, because of which I can take it. If this nums of I would have been less or equal to my reward sum whatsoever I have maintained so far, I cannot take it. Even if I want to take it, still I cannot take it. So I realized that I have two options: not take it or take it. In take it also, I will make sure I can take it only and only when my nums of I is more than my reward sum existingly. If that's the case, which means I can take it. If I will take it, I will move on. As you are not able to move on, but you can move on now to I plus 1, and then you will simply have your reward sum, existing reward sum, and now you were able to take your nums of I. So you are able to take your reward value of I. You were able to take it. This is the only two states, like only two recursive ways of your DP, that not take it or take it. That's it. Now, so you realized what you have in your DP state. You will have the index at which you will go on. You will also maintain the reward sum. Now, for many of you, you will have doubt, Aryan, index makes us feel like, okay, we can do it, and it can go up till 2000, because in the medium or the medium version of the problem, which is sequence 1, the constraints are n is 1000, sorry, n is 2000, and nums of I, which is reward value of I, is 2000 also. In the hard version, the constraints are increased. But let's focus on, can we solve our medium version by DP? For sure we can, because we realized, okay, I is 2000, but this reward sum, what is the maximum reward sum? Because so as to determine the complexity of the problem, you have to determine what is the maximum reward sum what you can get. Now, just ask yourself one thing. Your reward value is 2000, right? Obvious. Now you realized that your reward sum should, again, which means you will land onto a specific nums of I. Same way, you land onto a nums of I, and you realize your nums of I is 2000, and you realized also that this reward sum should be less than your nums of I. So it should be at max 199. As soon as you add it, you will get a 2000. Let's say it is 2000 only. Again, although it is 199, but yeah, let's say it is 2000. So maximum your reward sum went to 4000. As soon as your reward sum goes to 4000, you know one thing for sure, that there will be no nums of I which you can add now. So you realize the maximum reward sum which you can go, which you can achieve itself, will be 4000, right? Again, although it will be 39999, but okay, for rough complexity wise, we can say 4K. Thus, we realized that our this reward sum at max will be in the same order, which is n. So it can be, I can say, as 2n. So for me, the complexity, if I use DP, will be O of 2n square, or I can say O of n square. And we know that n is 2000, and it will simply work for us. Cool. Now, again, I've just given that why you should sort it. It's obvious that you have to take a subsequence, and that subsequence will say, okay, if you would not have sorted it, then you would have taken the sum as 1. For sure, 1 is less than 6, so you can again take a sum. Now the sum became a 7, but now you cannot take a 4, because 4 is less than my sum, and I can only take a number when the number is more than my sum itself. So that's the reason it is obvious that you should sort it, and that we saw in the beginning also. Now this is the array which will be after sorting, and then we can apply our entire DP on the sorted array. Cool. Let's see the code. It's exactly same as what we discussed, that firstly we will sort the array. Then we realized we need our array of, again, we realized our array will be of I and our reward sum. Now, if you look at how I've implemented my recursive approach, it will simply say, okay, solve. Now, firstly, we'll firstly, we always focus on the recursive approaches, like recursive methods. It is take or not take. If I take it, I again had a condition. I can take it only and only when my reward values of I, it is more than my reward sum. If that's the case, simply call for I plus 1, next index, and your reward sum is now increased to reward sum plus rewards value of I. And then again, this is constant, which is being passed again and again, just a call. But if it is less, if the reward value of I, it is less than or equal to my reward sum, then I know one thing for sure, I cannot increase my reward sum, which means my reward sum will remain as it is. But Aryan, this is a solve function, this is a value. No worries, bro. As you will see in the base case, I am returning the actual value. So this, I am making sure, okay, I will return something. This solve function will return something, it will be returned. So no worries. If I will not take it, simply go on to I plus 1. If I have not taken anything, so for sure the reward sum will remain as it is. And again, let's go on to the base case. For sure, we have to stop as soon as our reward sum becomes more than the maximum value of the array. And maximum value is at the end of the array because the array is sorted. Then I can simply say return the reward sum itself. I cannot go any further. I cannot even increase no matter what, because reward sum is more than the maximum element. So there is no element itself altogether which can add now in my reward sum. Now again, this is the case which will handle this when the reward sum increases. Other cases, okay, when the array itself is ended, because you know that you are going on to I plus 1, I plus 1, I plus 1. So at one point the array will end. If the array is end, look, if the array has ended, return the existing reward sum, whatsoever you have obtained. And that is my simple recursive approach. Cool. Now from the main function, I realized that my reward sum, or I can say my reward sum, this value can at max be my maximum element of my array. So I will just initialize with the maximum element of my array. So my dp is nothing but dp of n and my maximum element of the array. That is my dp. Initialize with -1. Cool. And ultimately calling from index 0 with the existing reward sum value of 0. And that's my answer. We realized that complexity of it, nothing but O of n into maximum reward sum value, which is nothing but maximum reward value itself. Same way for space. Now, this will pass for the medium problem. What about the hard problem? In hard problem, it will no matter pass, because if we see the exact same, it will touch my value of 25 into 1e8, which will TLE. Again, how I can solve it? That is very tricky, that how you will solve it, but just focus on the functional part, what you were actually doing. You were doing and trying to find all possible sums. Ultimately, what you were trying is finding all the subsequences. Out of all these subsequences, find the sum. That is what you were trying. And then ultimately, out of all those sums which you have found out, you will take the maximum sum. Now, if you had solved the same problem, although it is highly unlikely, no worries, we'll go on to the existing problem again back. But if you have solved this problem, in which it is simply, the problem simply says that you have a matrix, on every row you have to choose one element, and then you have to go down and try for all the rows. On every row you have to for sure choose one element, such that the summation of those elements what you have chosen is as close to as target as possible, thus giving us minimum difference with my target. And thus in this case, if I take 1, 5 and 7, my sum will be 13. That is as close to as my target, thus giving me the difference between my target and the sum which I have obtained as 0. And that's the answer. So in this, you will simply realize what you were doing. And at the first level, let's try for all the values. Again, I have diverted a little bit to this problem, just so that when I go back to the main problem, you will realize what is the exact use case, that how I figured out that BitSet will be used. Cool. Again, it's important. Only 5 minutes. So on the first level, I just took the values as 1, 2 and 3. That's a possible sums, right? 1, 2 or 3. On the next level, I have a 4, but I could have reached, again, this can be solved by DP also. So no worries, you can solve by DP also. That the same way we solved the existing problem above one, DP with the DP. So with 4, I can either pair it with 1, 4, 2, 4 or 3, 4. So I can say I can have 4 plus 1, 4 plus 2 or 4 plus 3, which means 4, 4 and either plus 1, plus 2 or plus 3. Same way 5 plus 1 plus 2 or plus 3. Same way 6 plus 1 plus 2 or plus 3. Okay, that is for level 2 possible number of sums which I can obtain. Same for level. Again, if I just write the same thing down, it will be this, it will be this, it will be this. For the level 3, what will happen? For this level, above level have all these possible sums. Okay, so my number 7 can be added to all the possible sums. Okay, adding my 7 to the first possible sum, then this possible sum, then this possible sum. So you realize one thing, you are kind of generating all the possible sums. Now, the fact in this is the possible sums will be at max something. So if I say, okay, number of values can be at max my 70 values here, and I know each value also can be at max 70. So I can bet on you that the at max summation values which you can obtain, different values, can be at max 4900. 70 into 70, because at each level I will take one value. And that is the main crux. When you have to try for all these summations and you are bounded by some number of summations, then you can apply and you can solve with this. Again, what you were doing, you were trying to take your previous row sums and making the new sums. Again, previous row sums, making the new sums. So it is kind of you're trying for the previous row and making the new row. And that is when you can use your bit operations. Aryan, how that the case? No worries. Let's come back to the problem and let's see that what our aim ultimately was. So it was a bit context switch, but no worries. Let's come on back. Now, existing nums array, I have simply sorted it. Now, in the very beginning, my sum is 0. When 1 came in picture, when 1 came for the first time, I will say, okay, 1 can come. Now, the possible sums I have is 1 and 0. Because 1 came, so I have a 1 here, and 0 for sure 0. Now, when 2 will come in picture, okay, when 2 will come in picture, I will see, okay, 2 can come as it is. That's one thing. But 2 can add in the previous values also. If I add a 2 in my 0, it will become a 2. If I add a 2 in my 1, it will become a 3. So 2 and 3 are the possible values when 2 get added. So this is when 2 came in picture, but I also realized, okay, these are now the existing values, which is 1 and 0. So 1 and 0, now these represent all the possible values of sums when I have taken nothing, 1 and 2. And the contribution of 2 is this, and the contribution of this is, again, existing one. Let's go on further. When 3 came in picture, again, when 3 came in picture, so if I add a 0 with a 3, I'll get a 3. 0, if I add a 1 with a 3, I will obtain a 4. If I add a 2 with a 3, I will obtain a 5. If I add a 3 with a 3, I cannot add, because nums of I should be more than my sum. This represents all the possible sums, and I can only add my nums of I to my sum only and only when my nums of I is more than my sum. And this is not the case, so I cannot have a 6 here. No. Okay, so the contribution of 3 is 5, 4, 3. But existing ones, okay, existing possible sums so far was also 2, 1, 0. So this is existing possible sums. So now the all possible sums, if I will traverse from here to here, are these. Same way, you can see I repeated the same process for when 4 came in picture, and the same way when 6 came in picture. Now, what did you see, or what did you saw from this? If I repeat the same process and ask you the complexity for this, you will say, Aryan, you are going on to all the numbers. That's what you were doing. You were going on to 1, then 2, then 3, then 4, and then 6, which means all the values of your nums. Okay, so O of n will for sure come in picture. Okay, O of n came in picture. But then you also said that, Aryan, I will go and ask for a specific, again, let's say I am trying to find the current number of possible sums for my, when my 4 came in picture, I will go and ask for all the possible sums of my previous, whatsoever I have got. And question is, how many possible number of sums can be there? So the question is number of possible sums, because at every process, at every integer or every number, at every nums of I coming in, I will combine my current nums of I with the previous number of possible sums. That will be the new contribution of my nums of I, and I will copy the remaining sums as it is, thus giving me the new number of possible sums for the current nums of I. Cool. Now, so what I do, okay, I have to go and find what are the maximum number of possible different sums which can be there. Okay. Now, again, coming on to the same funda what we saw earlier also, I have to add nums of I in my previous number of possible different sums. But if you have to ask number of a possible different sum, let's change the wording and ask what is the maximum sum possible, right? That's much more easier to find out the maximum sum value itself. So I have told earlier also that nums of I should be more than my previous sum, so that nums of I can be added to my previous sum. Now I know the boundation of nums of I is itself, because of the hard constraints, it is 5 into 1 is 4. So I can easily say that my previous sum should also be less than my 5 into 1 is 4. So I can easily say one thing, that new sum, which is nums of I plus my previous sum, can at max be 5 into 1 is 4 plus 5 into 1 is 4, which is 10 into 1 is 4, which is again 1 is 5. So 1 is 5 is at max the maximum sum value. Again, although for sure it will be 4, like again 4999, but still I am just simply saying that 1 is 5 is at max the maximum possible value of sum. Make sure it is not exactly this, it is 4999 like this value. Sorry, I should say 99999 like this value, just as the maximum value. So we realized the number of possible sums can at max be 1 is 5, because this is the maximum possible sum value itself altogether. Now complexity wise, and 5 into 1 is 4. Number of possible values of sums, 1 is 5. The complexity will be 5 into 1 is 9. Obviously will not work. Oh, Aryan, this will give us TLE. Okay, yes, it will give us TLE. But if I had this value, I know this is 5 into 1 is 9. If I would have divided by a constant, now this constant is 64. Aryan, from where it came in, no worries. But suppose it came in somehow, then it would have reduced to 8 into 1 is 7, which is less, which is much less. And again, a spoiler alert, what if rather than this 1 is 5, how this 1 is 5 came in? This 1 is 5 came in when you have 5 into 1 is 4 plus 5 into 1 is 4, which means 5 into 1 is 4 twice. If I would have rather taken just once, then it would have been only 5 into 1 is 4. So the complexity, this value would have changed to 25 into 1 is 8, again divided by constant, which is 64. Then I would have got a 4 into 1 is 7, which is again much less. And you will see that this will give you a runtime of 800 milliseconds, and this will give you 260 milliseconds less. But again, your question will be, Aryan, what is this picture? What is this 64? How did it even come in picture? Like, how did it even came in picture? This is nothing but your bit set will bring in picture. How to think of this? Because you have to generate all possible sums considering the previous sum, and that is exact same what we saw earlier also when we were seeing this problem that you have to generate all possible sums. Same way you are doing here also, generating all possible sums. And in this case, our bit set can be a companion to reduce the complexity a little bit, just so as to pass it. Again, this is actually the most optimal solution which I'm going to tell. So again, for the folks who don't know, BitSet is nothing but a Hindi version of bit, as an easy version of bit. So it simply says that, okay, you realize you have used your bit, but whenever you have used your bit, you have realized, okay, maximum you have used 64 bits, because you represent your entire bit values, which is the binary values, in a form of integer, and integer can be at max long, which is 64 bits. So okay, 64 bits, it's enough. But what about if I had to use more number of bits? Then when I say more number of bits, what if I want to use 1e5 number of bits, 1e6 number of bits? Then I use my bit set. This bit set helps me to perform exact same bit operation on a large array. So, but Aryan, if you are saying that you can perform the bits operation on a large array, rather instead take an array itself, right? Take an array of Boolean values 1 and 0, and then perform the operation by yourself. You might say, okay, if you perform the operation on this Boolean array of size n, it will be a O of n time. But if you perform the operation on a bit set of size n, it will be O of n by 64 or 32, depending upon the assembly language which you have taken. Now coming on back, for the folks who are using Python, please skip the next 5-10 minutes, because around I will explain all the properties of BitSet. So firstly, we realize BitSet is more or less same as that of your bits. So I can initialize and say BitSet of a fixed size. You have to initialize fixed size. You cannot give size on runtime. That's an issue. But yeah, no worries. That's what it is. So you will just say, okay, of size 8, initialize your bit set. It will simply initialize 8 values, 0, 0. Imagine it as an array. That's it. Imagine as an array with your bit operations you can apply on it. Cool. Now make sure one thing, array starts from left, but bitset starts, as we know, it starts always from right. Same property as of your normal bits. Same will be applied here also. It's just in a form of an array of size 8. Now, if I say, okay, initialize the array, bitset array with this 15 in the binary form is 1, 1, 1, 1. Array size is fixed, which is 8. So remaining are zeros. Okay. If I say with a string, help me to initialize it, simply I'll use a string 1, 1, 1, 1. Remaining, again, size is still 8. Remaining are 0, 0, 0, 0. Okay. So this is how I will use my bit set. Many operations are set, reset, flip, count, test, any, none, all, size, and 2 strings. Right? Again, don't need to memorize it. You can simply do a Google search. It is a GFG search which you can do. Cool. Now, more operations. Let's say you have all unset, which means your bit set is initialized with all zeros. So right now it is all zeros. When I will say that, do one thing. For initially all zeros, set at index 0. So what you will do? You will go on to the index 0, and you will make a set, which means you will do flip the bit, or you will set the bit, not flip it. If it is 1, it will remain 1. If it is 0, it will become 1. So now you have set the bit. That is the operation, what you saw, set. Right? Again, I will show a couple of ones which are most important. But this is not required because I'll show you one spoiler alert. You can use a all unset, which is again all unset, which is nothing but a bit set. Say the index value and put as a 1. That's equally applicable. Right? Okay. Coming on back. Let's say if all set is there, all set is all ones is there. Imagine you are saying just reset. It will bring it back to 0. Reset the index, bring it back to a 0. Cool. There's one more operation, convert to a string. So this bit set value is converted to a string. It is a 110, 1110. Convert to actual integer or actual long or actual long. Convert to a value by saying to your unsigned long. You got a long value. Cool. Although this is very, very less used, the ones which are highly used are these operations, which you apply on a normal bit array also, like normal bit values also. The operation is, let's imagine you initialized of size 4 your bit set. First is B1, next is B2. Cool. Initialized with 1001 and 110. 1010. If I ask you that bit set of 1, you will go again. This is the index 1 for the bit set of 1, which is bit set of 1. Go from the end, index 0, index 1. Okay, index 1, bit set of 1 says a value 0. Okay, it's a 0. Now do an AND operation between two bit sets. You can simply do, because they are binary values. Simply do AND between these two bit sets. So 1001 bit set 1, 1010 bit set 2, AND operation I will get a 1000. So I ultimately got the result as 1000. That's it. Again, simple and that too. Don't assume. Okay, Aryan, what's the complexity? Complexity for this will be, I'll tell you. But as you can see, the size for this is, let's say, n. Size for this is, let's say, again, n. Both are of size 4. Let's say n. The complexity for this will be O of n upon 32, or you can say O of n upon 64, depending upon what the compiler is. If it's a 64-bit compiler, 64. If it's a 32-bit compiler, 32. But if you would have tried this by yourself, if you have taken an array of Boolean values and then you have tried by yourself, it will be exactly O of n, not divided by a constant factor. That is the prime use case of your bit set. Cool. Coming on back, we have simply did a AND of bit set, no worries, but initialized bit set by 9 again. So you see, 9 is a value, but now it has become a 1001 back again. So I'll simply say bit set of 1 or operation. Simple, or operation with bit set of 2. I got the value. It is a result. Same way, I can do a NOT operation. Bit set of 1 did a NOT. I got a result. I can do a simple XOR operation. Bit set of 1, bit set of 2, XOR operation. I got the answer. I can do a left shift and right shift operation. Left shift. Okay, this is a very important thing. If I have bit set of 1, which is 9 right now, right? I did a left shift. You have seen the lecture. If you have not seen, if you have seen the lecture, you should be knowing what masking, left shift, right shift, and or is. If not, then please go and watch it. But if you know left shift, okay, this entire thing will be shifted to left. So if I shift it, okay, this 1 will come here, this 0 will come here, this 0 will come here, this 1 will come here. Now this was the window for my bit set which I have initialized. So 1 went out of the window, so it will be truncated. So this will the 1 right here will go away. Now whatsoever is empty is a 0. So this is what you have achieved after your left shift. Same way for right shift, you had this value. If you right shift, this 1 will come here, this 0 will come here, this 0 will come here, this 1 will be truncated, and thus you will get this value where 1 is truncated. This is your final value of right shift. So this is how you perform the operation. Now, this is a quick explanation from Stack Overflow that you should always remember the complexity depends upon your assembler, which means your compiler. It depends upon your compiler, okay? If it's a 64-bit, you will be dividing by 64. If it's a 32-bit, by 32. Cool. Now, coming on back, we have now learned about bit sets and bit. If you have not watched it, please go and watch it. Now, coming on back to our main problem, we will now use bit sets. How? Let's simply see. Again, so how we'll store bit set? We realized bit set simply starts from very end. 1, 2, 3, 4, 5, 6. So it is in my bit set vector. Let's say bit set vector initialized of length 7. Cool. Now I will keep a track of what all sums I have in this bit set vector. I will say, okay, if the sum of 0 is there, which means I have a sum of 0. If a sum of 1 is there, I have a sum of 1. If a sum of 3 is there, I have a sum of 3. If a sum of 2 is there, I have a sum of 2. That's how I will maintain my bit set vector. How I will use it? No worries, let's see it. But we realized one thing for sure, the maximum possible sum value can be at max 1e5. I'm maintaining my sum, so I should initialize my bit set vector with a constant value, which is 1e5. Okay, this one is not required, it is 1e5. Cool. Now, what I need to do, at every step, if you remembered, I was, okay, when 4 came in picture, he was asking the previous all possible sums, generating the contribution of 4, and then whatsoever was remaining, just copy as it is. Remember this line, I will repeat it again when I will dry run it. So what I will do now, I will dry run it. So what I did, I am at 4. I want the previous sum, all possible sum. So to maintain all possible sum, let's say I'm maintaining my DP value, which will say all possible sums. You can take it as any variable. Let's take it as a DP value. Now, this DP value will say all possible sums. And you can simply see, so far, all possible sums are 5, 4, 3, 2, 1, and 0. 5, 4, 3, 2, 1, and 0. Okay, this is my bit set vector. So, bit set vector initialized with 1e5 DP value. Now, you will say, Aryan, why you have taken other ones? No worries, I'll tell you. But I told you, whenever the 4 will come in picture, 4 can be linked with the previous all possible sums, considering I can take possible sums which are less than 4, which means I can take only these possible sums. Cool. So, remember what the DP value right now here is. DP value right now here is the all possible sum so far. And I'm trying to find the DP value of when my 4 came in, which means I'm trying to find a specific DP value, which will make me all possible new sums so far. Cool. So this is kind of my previous DP. This will help me to calculate my new DP. Cool. Now, coming on back, we realize one thing for sure, that we need to have a boundation, that how many previous, because it's a DP, it will tell me these are all the possible previous sums, but I have to put a boundation. Up till what point I can actually add my 4 in my previous sums. So to put that boundation, we realized we use what? We use masking. If you don't know, go watch this video. For boundation, we realized we will use masking. So I will put a mask. I will make a mask. Again, I will make a mask. That's the reason my mask was again of type BitSet, because I want to do a AND operation with my existing DP value, so as to obtain my possible number of contributions which I can do with 4. So I made a mask saying everything less than 4 is allowed. So I made a mask from 0 to 3, all ones. It is a mask. This simply represents that everything less than 4 is allowed. Now, for the Python folks, it's simply masking. Simply a mask if you want to make where all are ones. It indicates 0, 1, 2, 3. So it simply says you have a nums of I which is 4 right now, the current element. Take a left shift, you will have 1 and 4 zeros. If you do a -1, this 1 will go away, and for all these zeros you will have a 1 1 1. So it represents simply a mask. Although for us we cannot do like this kind of operation. We can do a left shift, but existing, again, I'll tell you, this is for a simple integer, but on the bit set, how I will make a mask, I will show you. But imagine that you have the mask where everything less than 4, you have all ones. Now, if this is all ones, what is the valid prev? Which means this was the DP, which was prev value so far. But you have to tell what is now the valid previous value. So everything which is more than my 4 will all become zeros. Everything which is previously a sum will become a 1, right? And again, here it could have been possible that this 2 would be 0. So it will be a 0. So it's a reason I will take a AND. So my valid previous will become my existing DP value and with my mask. And you realize why? Because DP contain all possible sum value. Mask will say my possible sum which I can take, which are less than my nums of I. And thus I will obtain my valid prev will say all possible sums which I have obtained which are less than my nums of I. Cool. Now when I've obtained this valid previous, I know I can simply now start adding my 4 in my these values. So I will obtain a 4. 4 plus 0 is 4. 4 plus 1 is 5. 4 plus 2 is 6. 4 plus 3 is 7. So I can obtain these all possible values. So let's simply, so what we did, we obtained, okay, we have a valid previous, which means these values. We can simply add a current value, which is 4. So I will simply add 4. I got these all values. What I did, I simply shifted all of them by 4 times. Because see, 0 shifted, it came to 4. 1 shifted, it came to 5. 2 came to 6. 3 came to 7. So in my bit set value, when I had my 0, 1, 2 and 3, I had 1, 1, 1, 1. I simply told, okay, 4, 5, 6 and 7. So I simply told, okay, this 1 should be added 4. So it will shift 4 times to the left. 1 will shift 4 times to the left. 2 left. 3 left. And thus I shifted everyone. When I say everyone, I mean everyone in the valid previous. I shifted everyone to my left 4 times. So I did what? To know the impact of my current nums of I in the previous possible number of sums which are less than my nums of I did valid previous left shift nums of I number of times. Make sure this is again a bit set and this is a value. How many times you should left shift? Now, when this is done, you have obtained what? You have obtained the contribution of 4. But what about the remaining? What about the remaining ones? Remaining ones, because I want the new DP. New DP simply says all possible sums so far. What about the remaining ones? Okay, bro. Remaining ones simply copy from the previous DP value. So I will say my impact from previous will be only DP, which means, okay, DP says the impact of previous, which is all this. I will simply take OR with my this value to get my entire values. So this is the impact of previous. I will take my new DP will look like my previous one doing a OR so as to take everything in impact, and this is the impact of my current element, which is nums of I. Now, this operation, whatsoever you have been doing with your bits or with your bit sets is all O of n divided by your 64. Considering it's a 64-bit compiler, and that is the beauty, but like that is the main crux of this, that you have achieved everything in just by using your bits. Cool. So this is how you'll obtain your new DP, and new DP is nothing but your DP new value, which is this value only. Cool. Now let's see the code. It's pretty simple, exactly what we have seen earlier also, that firstly I will maintain my DP value of 1e5. Again, this can be 0, 1e5, valid previous and my mask. So firstly, for a possible sum as a 0, I have one empty subset. So I have one possible sum. as 0. So when the sum is nothing, it's a zero sum. Okay, it's one possible thing. Like I have a zero sum. My DP represents all possible sums. I have a zero sum in the very beginning, right? Okay, cool. Then make sure your region, like your dharam, sort the array. Make sure to sort the array. Now I have got the mask ID. If you remember, you are making a mask. If you remembered, you are making a mask. You are making this specific mask, and this mask should be of length 4. Your mask should be of length 4. Now, there is no easy way to build this big of a mask entirely in one go. If it would have been an integer, it would have been possible. But now, to make this all ones, either you have to build a string of all ones, and that too, all ones can be equal to my nums of I, which means it can be equal to 5 into 1 is 4. So if you will repeat this process of making the mask again and again for all nums of I, you will get a TLE, because in worst case you are iterating on all the elements and then you are building the mask from scratch again and again, you will for sure get a TLE, because this will take O of n time, this will take O of n time, O of n square, for sure give you TLE. So what you will do? You will build your mask incrementally. How is it possible? It is possible because you have sorted the vector, which means the values are always increasing incrementally, which means 1, 2, 3, 4, 6. So initially the mask is only 1, then 1, 1, then 1, 1, 1, then 1, 1, 1, 1, then 1, 1, 1. Sorry, it should be 1 less, but yeah, you got the essence. 1, 1, 1, 1, 1. So with this strategy, you are only and only increasing your mask set bit. Thus, you are ultimately going on to all the set bit of mask just to build the mask only once. So that's the reason I am building my mask. And again, please don't confuse. This for loop and this while loop are just detached from each other, because this while loop in worst case will iterate until my entire mask is built. An entire mask can be built. It is limited by the value, and value can be at max 5 into 1 is 4. Thus, this thing, mask building separately, will take O of n time. Again, separately. It is not inside this for loop. Cool. That's the reason why complexity understanding is very important. Coming on back, let's imagine we have built the mask. When the mask is built, we will find the valid previous. Same way, existing DB value and the mask, I will get the valid previous value. And I will use my valid previous, I will left shift my value times so as to get my contribution of value in the existing sums. But I could have remaining sums left from my previous DP. So just do a OR with the existing DP and getting a new DP value. Thus, I will be getting my exact thing. Now, you have built your entire DP value, right? What your DP value indicate? It indicates your all possible sums, and you have to get the maximum possible sum. Simply iterate on your DP value from the end, which means from the maximum index. Go on. The first time you get a non-zero value, which means this index is the maximum possible sum. You went on from the very end, and the first non-zero value you got, that is your answer. Again, we saw the complexity of this. It will be simply as what we discussed already, which will work in roughly around 2000 milliseconds. It is high, but this is the only approach. And that's the worst part. It's the only approach. Now, one beautiful thing which can help you to improvise a little bit more, making it nearly about 300 milliseconds, is that what you are doing. And that's a simple trick which we used earlier also, that you are building this. Again, this bit set needs to be this thing needs to be constant. It needs to be constant. It needs to be initialized ahead. I cannot just say on runtime. I have to do initialization on initially itself. So if I can somehow make the size as 5,000, then I would actually optimize a lot more. The pruning will be done a lot more. But can I do it? Obviously I cannot. Why? Because I can achieve a sum which is for sure more than 5,000, and DP is storing all possible sums. So for sure I get a wrong answer. But can I find a hack around it? Yeah, obviously I can. Remember this thing which we have seen previously? Now, if I just tell you one thing, imagining you had your earlier sequence, You asked me to take a subsequence. Subsequence can be A, B, C, and D. Now for that subsequence, you are telling me that this will give you the maximum sum. Aryan, this again, remember, this is my sorted. I have just simply sorted it. You are telling me, Aryan, this will give you the maximum sum, which means okay, A plus B plus C plus D is the maximum sum. Now, if this is sorted, my argument is E will always be included. But you will say, Aryan, what if this entire sum is more than E? Then for sure, E will not be included. No. Why? Because I can simply remove my D in that case and can put a E instead. And I know E is always more than or equal to D because the array is sorted. So this sum, which is A plus B plus C plus E, is always more than equal to A plus B plus C plus D. Thus, what is the inference from this? The inference is that the last or the largest value will always be included in my final sum. So my final maximum sum, I can obviously and very clearly say that I will for sure have the last element, again last as that of sorted array, and then I will have the closest sum to my last element. I will add, because for sure I have to maximize my answer, so I will add something. I will add what? I will add something. Again, this will be your rev sum, right? Like reward sum existing, and this is your new element, nums of I. So you can only add your reward sum in your nums of I when this reward sum is less than your nums of I, which is the last element. So I am saying my reward sum will be closest sum to my last element, and that will give you that. Now you have to not find your sum like which can be like 10k. No, you have to find the sum which is closest to 5k. So your DP can now store at max the sum up till 5k, because I know the closest sum to the last element can be at max 5k. Last element can be at max 5 into 1 is 4. So the closest sum, I can also say it can be at max 5 into 1 is 4 minus 1 to be like more precise. But I can simply say it can be 5 into 1 is 4. And that's the beauty. Now I don't need to take the entire thing. I can take only 5 into 1 is 4. Cool. So what I will do, I will simply use the 5 into 1 is 4 thing. So I will now initialize by saying it will be 5 into 1 is 4. Cool. Now again, DP, my prev, again, if you are thinking, okay, Aryan, where did that prev, like valid prev went? Bro, valid prev was DP and mask. I'll simply just put DP and mask here in the like new code. So in the new code, I have put my DP and mask here itself. Cool. And then again, you did one thing, that you have to find your closest sum, which for sure should be less than your maximum element. So it can be at maximum element minus 1. This is your closest sum which you can achieve, right? Now, again, you will build your mask as we did earlier also. I will build my mask, same strategy. But now I will tell one thing, that I can do it only and only when, for sure, when my mask ID is less than my rewards of ID, which means I can for sure incorporate you. Then I will take you. Now, for few of you, you might think, okay, Aryan, what if I exceed this? Because for sure you can exceed. You can obviously exceed. If you're, again, it is some mask. It is a sum value of sums. You are doing a left shift by rewards of I. Rewards of I can still be 5,000, right? Sorry, 5 into 1 is 4. Why I always say 5,000? But yeah, 5 into 1 is 4. Left shifting something by this much value, for sure there's a high chance, even if I take a 101, still if you left shift by this much high value, you will simply exceed your boundary of bit set of 5,000. But Aryan, then I'm missing something? No, you are not, because your task only was to check anything inside 5,000. Again, imagining it is 0 to 5,000. So your task only was to check anything which is as close to as like 49999. 1, 2, 3. Okay, this was your task. So ultimately, if anything is going outside, which means truncating, you don't have to worry about it, because you only wanted in this range only, closest sum you wanted. And thus I will say, I will go backward and I will find the first non-zero value starting from this closest sum, because that's my boundary which I have taken, and that will be the maximum prev value or maximum rev sum. If I go back, that will be my maximum closest sum to my last element. And for sure, make sure to add the last element. So this is the last element and this is the closest sum to my last element. And thus I have got and reduced my complexity quite a lot margin. And thus my complexity is now just pruned. And thus having to not go on to like having a factor of 2. Like you can say it is now divided by a factor of 2. But still, the runtime is kind of increased, decreased drastically. Cool. I hope you guys got it. Again, this is a very big video because we learned in the basics of bit masking, the use of it. We discussed 2 problems indirectly. Sorry, 3 problems indirectly. One is sequence 1, sequence 2, and so on and so forth. Cool. I hope you guys got it. Again, this is a very long video. I wanted to finish it in 20 minutes, but there's no matter if someone can finish it in 20 minutes. I know I am very badly called in community for making long videos, but sorry. But yeah, this one I think needed this much explanation. But yeah, cool. If you guys liked it, then please smash the like button because it takes a lot of efforts to make this much stuff. Again, it took me around 4 hours now. I don't know why it took me more, but yeah, it took me a lot more. But yeah, cool. It'll be very helpful if you can just smash the like, baby, and don't forget the target by June end, 45K subs. We need to have it. We need to do it. All right, take care.